Every single thing around you right now, the chair you're sitting on, the light hitting your screen, the sound of this video, is governed by a set of rules. Rules so consistent, so precise, that we can write them down in a few lines of mathematics and predict the behavior of everything from electrons to galaxies. That set of rules is physics. By the end of this video, you'll know what physics actually is, why units matter more than you think, and how to handle numbers confidently the way every physicist does. Let's get into it. So, what is physics exactly? Physics is the study of matter, energy, and the fundamental forces that govern how they interact. That's the textbook definition. And that's correct. But here's the more useful way to think about it. Physics asks, why does the universe behave the way it does? And then it answers that question with mathematics. Physics sits at the foundation of every science. Chemistry, built on atomic physics. Biology, built on chemistry. Engineering, applied physics. Even economic models use physics-style equations. To understand physics, you understand the language the universe is written in. For exams, whether that's GCSE, A-levels, IBDP, AP, CBSE, or you're aiming for JEE, physics is not about memorizing formulas. It's about understanding why those formulas work. That understanding is what separates the students who can solve a problem they've never seen before from those who've only solved ones they've practiced. Now, the first practical skill you need, units. Here's the thing, in physics, a number without a unit is meaningless. If I told you a car was traveling at 30, you would have no idea whether to be impressed or terrified. 30 meters per second is fast. 30 kilometers per hour is a quiet country road. All of science uses the SI system, the International System of Units. There are 7 base units, but you'll use 5 of them constantly. Meter, represented by M, which represents length. Kilogram, K or kg, which measures mass. Second, or S, which measures time. Ampere, or symbolized by A, which measures electric current. And Kelvin, symbolized by K and measures temperature. Every other unit in physics, newtons, joules, watts, volts, is built from the combinations of these 5. That's why they're called base units, and the other quantities are called derived units. And then there are prefixes, shortcuts for every large or very small quantities. You need to know these cold. Nano is 10 to the power minus 9, micro is 10 to the power minus 6, milli is 10 to the power minus 3, kilo is 10 to the power 3, mega is 10 to the power 6, and giga is 10 to the power 9. So when you see a wavelength of 550 nanometers, that's 550 and 10 to the power minus 9 meters. When you see a frequency of 2.4 gigahertz, that's just 2.4 in 10 to the power 9 hertz. Converting these quickly and correctly is a mark gaining skill in every exam. Speaking of large and small numbers, let's talk about scientific notation. Because physicists almost never write out 0.0000000000167. Instead, they just simply write 1.67 in 10 to the power minus 10. The rule is simple. One non-zero digit before the decimal point, and then times 10 to some power. Here are some examples. So the speed of light is 300 million meters per second, but that's just simply 3 times 10 to the power 8 meters per second. The mass of a single electron is 0.00000. Who knows how many zeros? 911 kgs. But you can just put that as 9.11 to 10 to the power minus 31. In the radius of a hydrogen atom, that's 0.00. Who knows how many zeros that is? And 5.529. So in scientific notation, that says 5.29 10 to the power minus 11 meters. Alright, let's try yourself. Let's write 0.00456 in scientific notation. So as you can see, the number is 0.00456. So we have to find a number between 1 and 10. Sorry, 1 and 9. Yeah, 1 and 10, but it's not equal to 10. So if we write the power as 8 to 10 to the power n as scientific notation, it has to be greater than 1 and it has to be greater than 10. Well, it can also be equal to 1. That's also fine. but it can be equal to 10. Alright? Or it also represented like this, if you're familiar with intervals, something like this. That also works. Alright? So, what is the number between 1 and 10 that we can use to simplify in scientific notation? That would be 4.56. But how do we account for the decimals? So the trick is, if you have a decimal, if you have a number that's like less than 1, you count the number of zeros before the first non-zero digit, which in this case is 2, and we add 1 to that. So we take 10 to the power 3, but we make it negative because it's less than 1. So there we go. So you can even verify this. If we take 4.56, move it 3 times to the left, we get the same outcome. It's the same as dividing by 1000. So all in all, this is the answer. 4.56 and 10 to the power minus 3. Now, let's move on to significant figures. This strips up more students than almost everything else. So let's make it simple. Sig figs, or significant figures, tell you how precise a measurement is. If I measure a length as 2.34 meters, I have 3 significant figures, right? So if I say 2.34 meters, that's 1, 2, 3 significant figures. However, if I write 2.3 meters, like 2.3 meters, it's only 2 significant figures. Why? Because it's this and this. So there are some rules for counting significant figures. So for example, all non-zero digits, all of them are significant. So if you see the example of 1.34, all of these are non-zero, so it's 3 significant figures. Next, the zeros between non-zero digits. So if there's 2 non-zero digits, like in this example 1.04, the 0 or zeros between them are significant. So again, 3 significant figures. Now, the leading zeros are not significant. So basically, in this example 0.0034, there's the non-zero ones are significant, but these two are trailing, so they're actually not significant. So, or they're not trailing, they're leading, so they're not significant. So it's only 2. Next, trailing zeros after decimal are significant. So for example, in this example 1.40, 1 is significant, 4 is significant, and 0, since it's trailing and there is a decimal point, then obviously it's 3 significant figures. So for exams, give answers to the same number of significant figures as the data in the question, unless told otherwise. So usually it's either 2 or 3, but depends on the board or the exam. Now, let's do a practice problem. How many significant figures does 0.00470 have? Alright, so let's do this question. So obviously all the non-zero digits are significant. So 4 and 7 are significant. The trailing zeros are only significant at the decimal point. So this is significant because of the decimal point. And trailing zero, or sorry, leading zeros are never significant. So we have 3SF, and that's how we count significant figures. Next, let's talk about the orders of magnitude. Physics deals with scales that are almost impossible to imagine, from subatomic particles to the observable universe. Orders of magnitude let you compare these scales easily. Two quantities differ by one order of magnitude if one is roughly 10 times the other. A human and an ant differ by 3 orders of magnitude, 10 to the power 3. So as you can see, if this is 10 to the power 0, if it's like 1 meter, then an ant may be 1 millimeter long. So maybe somewhere around here. An ant, that's 10 to the power minus 3 meters. So as you can see, the difference between these uh, organisms, the size of these organisms, is 1,000 times, or 10 to the power 3 times. Why? Because they differ by 3 orders of magnitude. So this kind of estimation, called a Fermi estimation, is tested in IBDP, A levels, and JEE. We'll cover it in detail later in the series, but now you know the core idea. So, in summary, let's pull this together. Physics is a study of matter, energy, and the rules governing how they interact, expressed in mathematics. These skills underpin everything you're going to do in this course. SI units, so you know the base units and prefixes gold. Scientific notation, one digit before the decimal, and in 10 to the power 10. Sorry, 10 to the power. So, in summary, let's pull this together. Physics is the study of matter, energy, and the rules governing how they interact, expressed in mathematics. Three skills underpin everything you'll do in this course: SI units, scientific notation, and significant figures. These aren't exciting topics, but they are the foundation. Get them wrong, and you'll drop marks on every single question for the rest of your physics career. Drop a comment below. Which of these three skills you find the trickiest? Significant figures trip most people up, but I'm curious where you're at. If this was useful, subscribe. We've got the full physics course mapped out, one topic per video, all the way from basic mechanics to the quantum and nuclear physics. So next up, we're going to do scalars versus vectors. It's the first concept where a lot of students fall behind, so don't skip it. See you there.